Hi, my name's Hamid Hamatash, and today we are going to talk about decision making. But first, see if you can try and guess the music. The music comes from one of my favourite games, so we'll see what that is later on. Today we're going to be talking about quite a few different things, but two main topic areas. The first is decision trees, and the second are finite state machines. Decision making involves working out what to do next. Typically in a game or an AI agent kind of scenario, there'll be a range of behaviors that your AI agent can perform. And decision making is about trying to decide which one of those behaviors is the most appropriate thing to do at that moment in time. Therefore, the decision making system needs to work out of all of those behaviors available, which one should actually get executed. And that's decision making in a nutshell from the perspective of an AI agent. Decision making systems usually integrate with lots of other AI systems and game systems, so usually they are considered as a whole. The decision making process itself can vary from being really simple to extremely complicated, and really it just depends on the situation and the type of AI that you're going for. If you're making an enemy for Mario, for instance, then usually the enemies are very, very simple. A Goomba, for instance, it really just goes towards you. And in fact, it's kind of more like a steering behavior than any sort of decision making. But you consider a boss in Mario with multiple states and behaviors, and when it should actually execute one over another, then it's using a lot more information. So even within the same game, there can be quite a difference in terms of the amount of variety you get in enemies. AI agents' decisions can only use internal data if you want, and that means that they can only use things that they have sensors for. So if the enemy has hearing or sight, they can use those sensors. However, in a lot of game AI, we try and cheat to save on performance, and therefore they can use external data, which is cheating. Basically, if the enemy or the AI does not have or should not have a specific bit of data, but you give it to it anyways in order to speed up something, that's totally fine too, and that is an AI agent that uses external data rather than internal data. Let's talk about decision trees, which are our first decision-making system that we can employ. A decision tree is a flow-like structure in which each internal node represents a test on an attribute. Each branch represents the outcome of the test, and each leaf node represents a class label. The paths from root to leaf represent classification rules. Now, this is a more formal definition of a decision tree, and it's definitely something that you should remember for future use. However, it's a bit terse and doesn't really get to the simplicity of a decision tree. This is an example of a decision tree in a diagram format. Each diamond is a decision point, and at each decision point, there are branches that come off each decision. A test usually happens in decision point, and this allows it to go down one of two branches in this case. After we've went through a few decision points in this diagram, for instance, you will get to an action, which is this rectangle. And in this action, this is where an AI agent would actually perform the final action that it should actually do. So we have a little test case here. The thing I want you to note about this is it's very important to see the structure of this decision tree and what each single type of element does. So we have diamonds that perform tests. We have the rectangles that are the actual actions and the outcome of the decision tree. And we also have the transitions. The transitions are the lines that connect the decision points together or from a decision point to an action. The transition basically tells us what happened in the test and therefore how it transitioned into the next part of it. This is a very simple decision tree, and it's probably better to have a look at how we would code something like this. Therefore, let's have a look at some pseudocode. So as you can see, the pseudocode on the left-hand side looks very, very simple. If we sort of walk through this, you can see that the first test, which is this one, is enemy visible, is just an if statement. We perform a simple if statement, enemy visible. If it were visible, and we go down into the next decision point here, you can see this decision point is represented right here. Enemy less than 10 meters. Is enemy less than 10 meters away? If that was a yes, we would go into the conditional part of that if clause and do the attack. And here would be some attacking code for your AI agent. If, however, it was a no, we'd come down into the next part of this tree and onto the next if condition. So the test would be, is enemy on flank? If it was, it would move. If not, then it would attack. And you can see this. So all the decision tree really is nested if statements. It's nothing more complicated than this, and this is the most basic thing you can do with AI code, is just to put some if statements together in sort of like a tree nested kind of structure in order to get what you want. And that's all we're really saying with a decision tree. It's nothing more complicated than that. As you saw in that previous diagram, decision trees have many decisions in them, and most decision trees are actually binary. And this makes sense because we are representing decision trees with if statements, and if statements are binary. If the test is successful, they go into one part of the if clause. If it's not successful, then they'll go into the else clause of that if statement. So we can model decision trees with if statements very easily. A decision tree can use the logical AND operator in order to get to its actions. So in the first part of this decision tree right here, if A and B, then action 1, therefore A has to be true, B has to be true in order to get to action 1. Otherwise, any other result would give us action 2. So the else clause, if you like, of those if statements would always go to action 2. You can also use logical OR. And for logical OR, all you have to do is, if one of the clauses is true, then we would go to action 1. Therefore, if A was true, then we'd go to 1. If B was true, we'd go to 1. Either one would be fine. If both were false, then you'd get to action 2. So there's nothing really more complicated than that, but it kind of shows you can reorder your statements in order to use logical ANDs or logical ORs within your decision trees. Decision trees are not only limited to just 2 branches though. They do not have to be binary. A decision tree can have multiple actions. So in this first diagram here, we can see that there's 4 transitions coming off this decision point and therefore into 4 actions. And you can represent this quite easily with an array in a for loop. Instead of using those if statements, you'd use an array in a for loop to go through as many actions or as many transitions that are in that array. And your decision point becomes just a little bit more complicated in that it has to loop through that for loop and that array in order to test each single action in turn. One thing to note with this is that a decision tree that has multiple branches can always be decomposed back into its binary format. You do have to rearrange the tree somewhat, and therefore your if statements, and in this example we can see that here. So we have the same tree as the first one, except it's been decomposed back into its binary format. Therefore, you can see that You can see that we then test one decision point, then onto the next decision point, then onto the next decision point, and so on. This leads us to this interesting question. We have an unbalanced decision tree on the left, and we have a balanced decision tree on the right. Which one is quicker to traverse? Pause the video, have a think about this, try and see what you think would be fastest, and then unpause the video and get the answer. So please take a minute to do that. The answer to this question is a bit more complicated than it may first seem. Consider action A, for instance, and therefore the test that relates to action A. In the first unbalanced tree, if the decision point was a very, very fast and cheap operation to do, then the unbalanced tree would probably be quicker, especially if A was going to happen 99% of the time. Because if you have a look at the balanced tree, it'd have to go through a few different nodes in order to do it. It'd have to do 3 tests before it would get to node A. Whereas in the unbalanced tree, that's not the case. The first test would lead to A. So if A had a 99% chance of always being the one that was going to be executed in terms of its action, then the unbalanced tree is going to be much, much faster. However, if the probability of any of these was kind of equal in terms of which actual action would actually get executed, then the balanced tree is actually quicker and more efficient, as it will always do 3 decision points to get to any action. Then the unbalanced tree, you could have to do all 7. So the answer to this is quite a bit more complicated than it first seems. The probability of decisions matters. Which of these actions is most likely to happen? If you know that if a particular scenario is going to have action A, B, or C happen most often, then you might choose the unbalanced tree. However, it's not just about the probability, it's about the computational complexity as well. What if A had the most expensive test to do? Then you probably wouldn't want to run that test all of the time. You would probably definitely not want to run it as the first one each single time either, which would happen in an unbalanced tree. Therefore, in order to make a decision about which type of tree suits your particular problem, it really depends on the probability of each action occurring and the complexity or the computation time it takes to perform the test in order to deduce which action should happen. So it's very important to consider the traversal of a decision tree when you are coding your AI algorithms. Up to now, we have seen static decision trees. That is, decision trees that will lead to the same answers depending on the test conditions given. However, a decision tree does not have to be static. Branches can be tailored to go down one over another depending on anything that you want. And in some cases, that could just be randomization. So you could use a flip of a coin, for instance, in order to do one action over another action. The tests do not have to be based on any sort of reasoning within the game world. It could just be the fact that you need a different sort of behavior to happen every so often, or maybe all of the time. Therefore, random is quite suitable for that. Therefore, we can introduce a random element into this, and then in this case we have a coin toss. So flip a coin. If it's heads, do one action. If it's tails, do another action. However, you have to note that decision trees are mostly executed every single game frame. Therefore, you have to sort of put in some sort of safeguards to prevent the AI from flip-flopping between actions. So you could imagine if this decision tree was executed every single game frame, it could alternate very, very quickly between standing still and patrolling if it was not under attack. So you have to be quite careful about introducing random elements into this, and to prevent oscillation like that, what typically happens is that you kind of lock the action that it's doing for a set amount of time. Therefore, you might have another set of conditions within this that pretty much specify that if you are in a particular state, let's say the patrol state here, because you've got a randomized heads coin toss there and you went into the patrol state, you might say, well, for the next 30 seconds, I'm going to go into the patrol state and just remain in that state. Or you could maybe say something else along the lines of, if I'm in this particular state, then I will remain in this state until another section of the decision tree has become activated. So there's a few different ways you can deal with things like that. Obviously, your decision trees become a lot more complicated when you start adding elements like that. However, I just want to state that a decision tree does not have to be static. It can use random in order to adjust which actions it will actually perform. Now we have come to our decision tree properties. Like every single technique I'm going to show you in this module, I like to show you the pros and cons of that specific technique. Therefore, for decision trees, the pros are they are simple and quick to create. They're just a few if statements after all. They're computationally efficient. They're very efficient, in fact. They are just if statements nested together. You can't really get anything faster than that. They're memory efficient. They take up no memory because the if statements are actually coded into the executable of the program. Therefore, there's no other data to really rely on or are needed for these decision trees. And they're simple to debug. Very easy to debug some if statements. However, there are a lot of cons. They can become really, really big very, very quickly. Have a look at this decision tree on the screen, for instance. There's not really that many decision points. An AI can have a lot more than this. So I wouldn't say this is a lot at all. And you can see already just with that amount of decision points, it's getting really complicated very quickly. The biggest downside, I guess, is that they're hard-coded. So this means it's difficult for designers to actually change these. If they want something changed, they have to ask the programmer in order to do that, and therefore the programmer has to spend time working out what the designer wants and therefore translating that into the actual tree itself, which is quite a time-consuming process. And related to that is that they're not maintainable. So if a designer, for instance, wants a big change and that upsets a major portion of the tree, everything under from that point at which you need to adjust will have to become fixed in some way in order to get it to work again. So it can be a really big headache to change these things. That's decision trees. And now we're going to move on to finite state machines. A finite state machine is a device or model of a device which has a finite number of states it can be in any given time. It can operate on input to either make transitions from one state to another or to cause an output or action to take place. A finite state machine can only be in one state at any moment in time. And that's probably the biggest thing that we'll see going through these further slides, is that a finite state machine can ever only be in one state at a time. That's its biggest advantage and also its biggest disadvantage. The most famous finite state machine is the hypothetical Turing machine presented by Alan Turing in his paper on computable numbers in 1936. Here we have a simple diagram of a finite state machine, and I'm going to explain what each of the elements in this diagram are. Therefore, the black dot represents the starting point of the finite state machine. It represents which actual state is the starting state. The arrows represent transitions from the various states and the direction they can travel in. The text along the transitions tell us the actual condition that's needed in order to make a state go from one to another. And obviously the rounded rectangles are the states. Here we have our finite state machine, and here's the pseudocode for this finite state machine. As you can see, it's actually quite simple. On the left we have a bunch of if statements. Again, it's nothing really that complicated. On the right we have the switch case version of it, the same thing. So let's talk a little bit about this. We have a state variable. This state variable could be any sort of data type that you want. It could be an integer, it could be a class. In most cases, they are enums, so enumerated types, which allow you to give names to particular values. And this allows you to identify the state a lot easier. The main thing is that we have a variable to keep track of the state of the finite state machine. Then we go and test to see which state we are actually in. Therefore, if we were in the guard state here, this condition would go to true, and we'd fall into this section of code. Inside this section of code, you can see that we try and perform 2 tests to see if we are going to transition to another state. We can see that we test the see small enemy condition, which is right here. And if we did actually find that to be true, that we did see a small enemy, we would set the state to be the fight state. Then on the next game loop, we would come back round and we would test, are we in the guard state? Well, we would not be in the guard state in that case. We then test, are we in the fight state? Well, yes, we are. And we would probably do something like an action to actually make the enemy fight. However, you can see if we were in the fight state, it can only transition to one other state, which is the runaway state. Therefore, we would test to see if we are losing the fight. If they were, they would go into the runaway state. And therefore, it would transition into that. As you can see, this is quite basic stuff. The main points of this is that within each of these states, you have to check to see if you should transition to the other states. That's the main thing you would do. The other thing you would do while you are in this specific state, you would actually perform some sort of code that is useful to your AI agent there as well. Therefore, if you were not going to transition to any other states, you would then run some useful code. Like again, if we were in that fight state, for instance, we would make our AI fight. The switch case version of this is the exact same, it just looks a little bit easier to read. That's one of the reasons why switch cases are used quite often with state machines, is it's just that it's a lot simpler to read. You can see quite clearly that I'm in this state. The case basically tells me I'm in the guard state, and you just do the transitions again. And you can see all other states a lot more clearly. It doesn't really save you lines of code or anything like that, it just makes it a little bit more readable. Some important things to consider: always plan out your finite state machine. If you don't draw a diagram out of your finite state machine, it's quite likely you're going to get it wrong. And if you get it wrong, that means debugging and extra time that you're going to waste. So always have some pen and paper beside you and just do a very, very quick sketch of what it is that you want to actually happen. Therefore, this allows you to plan out all of the states that you actually need and consider all the transitions that are required. Quite often, if you just dive into the code, putting this stuff in, you will code something, it will look like it's properly working, and then a little bit later down the line you realize you forgot to deal with some certain transitions, or maybe you missed out an extra state that you hadn't really thought about. Those types of mistakes can be avoided if you just plan out the finite state machine on paper. Therefore, let's think about all the inputs you need into those transitions. And again, want to really state the obvious here, but draw it out. It really, really will help you find the design flaws in your finite state machine. It's going to be a lot quicker to implement in the end, and you'll have a clear mental picture of how it's supposed to function. And this holds true for a lot of code, and especially AI code at that. If you plan out the thing on paper first, you can actually save yourself a ton of time and work by not falling into obvious traps which you could have avoided. Some properties of finite state machines: they're quick and simple to code, as we've seen. They're a bunch of if statements or switch case statements. They're easy to debug because for the same reasons. It's very easy to step through code when that's just plain if statements or switch case statements. They're computationally efficient again. They're just if statements, and they're quite intuitive. It's quite easy to see where you are and which state you are in at that moment in time, and it's quite easy just to work with. So they're really good for that kind of thing. However, there are some cons. They don't scale well, and what I mean by that is that once you have lots of states, then it can become a bit difficult to manage. The other con is that they can only be in one state at any one time, which means that sometimes you might have an AI agent that has to be in two states, and therefore to try and mitigate that or deal with that scenario becomes a bit of an issue, but we'll get onto that. It can be quite labor intensive. What I mean by that is that as you start typing all this code out, it's actually quite a fair bit of code to deal with all the different types of transitions and all the different states and make sure that they all work with each other. One thing that you'll find out quite quickly is a lot of people tend to copy and paste their states because it seems like it's a quick option, but in the long term, it's actually a really bad option because you'll make mistakes, you'll forget to change variable names or the actual transitions, and the AI will then not do what it's meant to be doing. The biggest problem, and which highlights all of these factors, is that there's no standardization. Each finite state machine is a custom entity in itself, and therefore it is not reusable. This brings us on to object-oriented finite state machines. In object-oriented finite state machines, the states can be encapsulated into discrete objects, classes, in order to improve on the standard design of the finite state machine. This is usually achieved by creating a base class, which all other states derive from. And you can probably see where I'm going with this, that if you have a base class and deriving from these states, that means that all that functionality you have in that state can be inherited and later down the line, and therefore you don't need to keep implementing every single transition or state or feature of that state. You can just inherit from it and use what you need. Therefore, it allows a common interface and allows extra functionality to be added, such as an enter state. Every single time you get enter state, sometimes it can be quite a handy feature to know that you've entered a particular state. Therefore, you might want to run some code as soon as you've went into the state for the first time, for instance. The update state could be added. Therefore, every single game loop, as you're in that state, you'll get a function call to say that you're inside that state. And if you know you're inside that state, it means that you can keep your code nice and tidy and contained to that method. You might want to add an exit state. As you leave a state, you might need to clean up some variables that are being held in that state, for instance. Or if you're doing something like trying to communicate with another class, then this is the time we do that in. Pretty much anything. You can add whatever you like into these things, and you can add more types of features as you see fit. And the reason for that is, as states are just objects now, which are just classes, new ones can be added very easily, and you don't have to change the whole code base, just the one that you're working on. Therefore, what does an object-oriented finite state machine look like a little bit? Well, like this. You usually have a class called a state manager class, which will hold all of your states, and it will also usually be responsible for updating all of the classes that you have. So this is kind of like a record keeper, if you like. It knows which state is active at this moment in time. It has a list of all the states that can transition to, and therefore when a state's requesting to change to another state, you would inform the state manager to do that for you. It would then change it, update the references and so on, and therefore keep everything nice and contained and very clear as to what is going on. One thing I do have to mention is that the states themselves contain the transitions to go to the other states. So that would mean like the actual if conditions that are being checked to see if it should transition to another state. And if it does, then it would do a function call into that state manager to say, okay, let's change the state. And that's pretty much it. And in this example, we have our state manager. We've got a base class state, and then we've got a guard state that we've derived from that base class state. And you know, if you wanted to reuse some properties of that base state, for instance, that would be perfectly legal within the guard state. And as you can see from that, that can help you prevent a lot of the copy and pasting from the old finite state machine type of code, and allows it to be a little bit more self-contained and encapsulated. Some properties of object-oriented finite state machines: they're simple to code, they're easy-ish to debug, they're not much more difficult to debug than a standard finite state machine. They're still quite intuitive, they're flexible, the states can be swapped easily, states can be reused. However, we still have some of those cons. They don't scale well. As you keep adding and adding these states, you're going to have a lot of them, and therefore to manage and know which one you're in, although we have that state manager class to help with that, it still can become quite tricky. You can only be in one state at the same time, and you might see a pattern here with a finite state machine. And it's also labor intensive. For each single state, you have to create a new class in order to represent that state. That means you're going to have a lot of classes. Now beware. With finite state machines, there's something called an alarm mechanism. This is something that interrupts the normal behavior of a finite state machine, and it causes every single state to have to respond to something that's important. Therefore, that means every single state has to be able to change to that important state and back again at any moment in time. And we have these two state machines at the bottom here. So the first one is without the alarm mechanism, the one in the bottom left corner. And the one on the right side of the screen, this one, you can see has this alarm mechanism. So in this example, it's got this get power state, which you can see is replicated for each single state in this state machine. And that's the horrible thing about an alarm mechanism, is that these states, the state that's so important that needs to be executed from any state that you're currently in, means that you're going to have a lot of code duplicated in your finite state machine. You're going to have to write transitions from each of these states to get to these get power states and then back again. What's even worse is the fact that these get power states are not reusable. As we have seen from the object-oriented finite state machines and the normal finite state machines, the transitions are actually contained in the states themselves. So these three states have to hold these conditions, these transitions, to get to these states. And likewise, these states have to hold transitions to get to these ones. Or else how would it know to transition back to these original states, these three states here? So this is the problem. Quite often you have an alarm state, usually if your AI agent's under attack, for instance, and regardless of whatever it's doing, it might be patrolling, it might be resting, it might be sleeping, it could be doing anything. But if you needed to transition to attack mode straight away because it's under fire, for instance, then whatever states you had in it are going to have to transition to that state and then back again. And there's no real mechanism to deal with that. To solve the alarm mechanism issue, a hierarchical finite state machine can be used. And as you can see here in this slide, this is a lot cleaner than what we just had in the previous slide. And the main reason for that is that a hierarchical finite state machine actually stores which finite state machine it is currently in. So we have two finite state machines here. One we've got called clean up, and just to go back to diagrams again, the state that these finite state machines would start in are represented by this black dot. So this means that we will be in the cleanup state for this particular finite state machine. And this H star denotes which point of the hierarchical finite state machine's state it will actually be in when it starts. So it will be in a search state here. Now, this AI agent can go about its business, trying to see trash, head for the trash, get the trash, go to the trash compactor, dispose of it and go back to its search routine. It can keep doing it as much as it wants. And if it needed to get power because its batteries ran out, for instance, then it would go into this new finite state machine called get power. And this finite state machine could be another one of these. It could have many components inside, many different states and transitions. In this diagram, it's only represented as a single rectangle here because that's all it's needed for this example. The key thing with this is that once this finite state machine transitions to this finite state machine right here, it will save a variable to say where did it come from, and therefore it will save a link back to this finite state machine. Therefore, when this is done, this action has been completed, the get power, it's recharged, and it wants to transition back. Therefore, it has saved a state of which finite state machine it should go back to, and therefore it can just go directly back into that regardless of which state it was basically in. And that's the key thing here is that when we left this finite state machine, we will have left in one of these three states. And because we're just transitioning back to this high level finite state machine, it will return to exactly where it was. So if it exited in the search state, it would return to the search state. If it was in the head for compactor state, it would return to the head for compactor state after it had got its power. And that's the real benefit of a hierarchical finite state machine. You can also have direct transitions in a hierarchical finite state machine. It's the same sort of process. You can have different states and you can actually go to external states. Every single time you transition from the hierarchical finite state machine to an external state or finite state machine, it knows where it came from and stores the variable of which finite state machine it actually came from, so that once it gets into another state that's external to the one you were in, it can just go and revert back to the one it was in. Some properties of hierarchical finite state machines are that they're scalable, they're intuitive to use, they're flexible, you can swap the states, reuse them, and in actual fact you usually use inheritance with hierarchical finite state machines as well. The other thing is that most of the time with hierarchical finite state machines, you combine them with object-oriented ones too, so you get the benefits of both. The states can be reused. It deals with the alarm mechanism very easily. The cons are that it can only be in a single state at any one time, like all finite state machines. They can be quite difficult to debug, as now you've got this extra complexity involved in knowing where it came from. Therefore, to try and navigate in what state you ended up into, you have to go through multiple levels higher above. And therefore, that makes them more difficult to understand and read. Now we've reached our two main decision-making systems. We have decision trees and we've got finite state machines. And these are really your bread and butter of coding any sort of AI agent. You're going to be using these regardless of what you use elsewhere. You might have Steven behaviors and these. You might have a whole ton of other AI systems, which we'll get into in later lectures. All of these things can be combined together to get the AI agent that you need. So it's worth trying these out and practicing and seeing how to actually create these things, because you're going to be using them a lot. We have a whole bunch of alternatives here. I'm not really going to go into any detail on any of these. Some I'll cover in later lectures, some I won't. The main thing is that you know that these things exist so that you may then go and research them in the future. So we have fuzzy logic at the top, behavior trees, utility AI, neural networks, planner systems, and bespoke systems, which just basically means anything that you can come up with. Some notable ones in this list, however, are behavior trees and utility AI. They're used quite a lot in game systems right now. Planner systems are also used often, mainly for things like real-time strategy games. You could imagine StarCraft 2, for instance, using that kind of stuff for its AI planning and attacking systems. Neural networks are also quite notable, as in normal computing. Neural networks are used quite heavily, especially in machine learning. Some further reading for you. The top 2 links here tell you how to create finite state machines and go through in quite a lot of detail some of the pros and cons of them. So it's well worth checking these links out. The bottom 3 links are for future things for you to look into. Behavior trees for AI and how they work. That's quite an interesting article. We've got utility AI as the next one down. That's again quite an interesting read. If you're looking for something really meaty to sink your teeth into, then the bottom paper is a look at a planner system, and you can see how sort of complicated they can actually become. Well worth a read, however not essential. Now we're back at Guess the Music. This is one of my favourite games, or rather it's a song from one of my favourite games, so let's see if you can guess it. The answer is, it's Ken's theme from Street Fighter 2. It's an awesome game, an old game now, but obviously there's many different versions of Street Fighter, with the latest one being Street Fighter 5. This particular song was by Mega Driver. They are a Brazilian metal cover band of game music, so well worth looking out if you want something a little bit different, and other details on the screen right now. Thank you for listening, and goodbye.